All right, so we're in section 5.5, and we're going to talk about indirect proof. And indirect proof is, it's different, not a little, it is different than what we've been doing so far. The kinds of proofs that we've been doing when we do the two-column proof, that kind of thing, we're doing what we call a direct proof. We start with something we know is true and figure out step by step by step what the next thing has to be true. What's another thing we know is true? What's another thing we know is true? So at the end we have something that we know has to be true. Indirect proof, we kind of go the other way. We're going to use what we call indirect reasoning. And we call it indirect because it's the opposite of direct reasoning, where we go step A, step B, step B, step C, step D, and we're done. Indirect reasoning means we consider a possibility, we think of something. I'm going to say think of possibilities. And then we prove them wrong. Until only one is left. So indirect reasoning is kind of what happens often when police are solving a crime, or when lawyers are arguing a case in court, where they say this couldn't happen and this couldn't have happened because of this, so this had to have happened. So what we're going to do is use indirect reasoning to do what we call an indirect proof. So for an indirect proof, it's different than what we've done before. We assume the opposite of what we want to prove. So that's our first step. And then we show that leads to a contradiction. Now let's stop here for a second and talk about this word contradiction. What do I mean by a contradiction? An opposite is essentially it. So if I said, oh, today's Friday, what would be a contradiction?
Thursday.
No, Mr. Beamer, it's Thursday. That would be a contradiction. And why is it not Friday? Because it's Thursday, right? That shows why that's a contradiction. So that would be our proof that our assumption was wrong. That I'm assuming today's Friday. No, it's not, because it's Thursday. That's a contradiction. And the fact that we get a contradiction shows that what we assumed has to be wrong. And if what we assumed is wrong, we've assumed the opposite of what we've tried to prove. So that means the original has to be true. All right. All right, so what I want to do next is we'll talk about we'll do some practice with assuming the opposite, finding contradictions, and then we'll do one really easy indirect proof. Just as an example of something that we use, that you may be familiar with, that use indirect reasoning for, is Sudoku. So you say, oh, I'm going to put a 2 here. Let's see if that works. Well, if a 2 is here, then that means a 3 has to go here, but that means a 4 has to go there, but that messes up the 4 that's in this row, so that can't be a 2. That's a way of doing indirect reasoning. So you try something out, you say, I'm going to assume that a 2 goes in this square. Well, what does that lead to? Well, that leads to a 3 going here and a 4 going there, but wait, a 4 can't go there, so that square can't have a 2 in it. That's indirect reasoning. All right, so let's do some practice. For all of these examples, we want to know what's the first step in an indirect proof. So first example. An integer, we want to prove an integer is divisible by 2. So first, what's an integer? Do we remember what an integer is? It's a number, yes. It's a special kind of number. It's a whole number, and they can be positive or negative. So plus or minus 2, plus or minus 3, so whole numbers. That's what we mean by an integer. And divisible means that 2 divides into it even. So we want to prove that an integer is divisible by 2. What would be our first step in an indirect proof? What do we want to assume? We want to assume it's not. We want to assume the opposite. We're assuming the opposite of what we want to prove. Assume it is not. Divisible by 2. So that would be our first step if we were doing an indirect proof. And then what could we do? What could we do to show that this leads to a contradiction? Prove it wrong. And how would we prove that something's not divisible by 2? How would we prove that that idea is wrong? Divide it by 2. Does it work? So that's all we would have to do, is try to divide it by 2. All right, so that would be our first step in that proof. How about 2? Let's say we have a class with 30 students. And we want to prove there are at least 16 right-handed students. So that's what we want to prove. Prove that there are at least 16 right-handed students. Well, what's another way of saying at least 16? Greater than or equal to? So greater than or equal to 16? What's another way of saying 16? Greater or greater than or equal to 16, at least 16? What's that? Someone said something? How many would be possibilities? How many students would be possibilities if we have 16 or more? Half. Would 16 be a possibility? Yeah. 17? 18? Yeah. So could we say 16 or more? So I'm just talking other ways that you might see this. Greater than or equal to 16, 16 or more. So if we wanted to do an indirect proof, what would be our starting step? What would we assume? What's the opposite of 16 or more? Greater than or equal to 16? At least 16. Less than 16. And what did you say, no? 15 or less? And you said, didn't you say something earlier for no more than 15? And in this case, how would we prove that what we're assuming is not true? How could we? Ask the students, count them, right? Count them. How many are right-handed? How many are left-handed? And that would tell us that the assumption, whether or not the assumption that there are less than 16 would be true or not. Let's do one more. We want to prove that angle A is a right angle. What would we assume here? Not greater than, or, and what else? Or less than. So how could we put that all together? Angle A. Angle A is not 90 degrees. Yes. That's just when we do an indirect proof, that's how we want to start. So we're just practicing on what if we're trying to prove something, how do we assume the opposite? This is just the first step. We're just talking about the first step. So then now let's talk about the second. The second step is show that leads to a contradiction. So let's try picking out contradictions. So this would be our first step in an indirect proof. Assume the opposite of what we're trying to prove. So let's find the contradiction in these next sets. So what I'm going to do for these is I'm going to list three things, and we want to find the two that are contradictions. So a triangle is acute. And what do we mean by an acute triangle?
Less than 90 degrees.
All the angles less than 90 degrees. A triangle is scalene. Do you remember what scalene means? No sides are equal, so no angles the same. And 3, a triangle is obtuse. So which two are contradictions? Which two cannot be true at the same time? 1 and 3, right? The triangle can't be an acute triangle and an obtuse triangle, because the obtuse triangle has an angle that is greater than 90 degrees. Good. And this says that all of them are less. So 1 and 3 are contradictions. So if we were doing an indirect proof, and at one point we said, well, the triangle is acute, and then we figured out that something else tells us that the triangle is obtuse, we would have a contradiction, and that would show that what we assumed was not true. This one's a little trickier. I like this one. I'm going to say for this one, triangle ABC is a right triangle. And what does that tell us about the triangle? It has a 90-degree angle. Measure of angle A is 60 degrees. Measure of angle A equals the measure of angle C. Whoops. It should be measure angle A measure of angle B equals 90 degrees. So we're starting with a right triangle. And we want to know which of these two are contradictions. So Noah says 1, 1, and 2. Why would those be contradictions? Perfect. So what Noah says is if A is 60 and C is 60, together that's 120. What does that leave for the other angle? 60. But we said that triangle ABC is a right triangle. So 1 and 2 are contradictions. Can we have measure of angle B equal 90 and the other two angles be the same in the triangle? Yeah? What are the other two angles? What would they be then? 45. We can have a 45, 45, 90 combination in a triangle. So 2 and 3 work together. And 1 and 3 work together, right? One can be 90, the other can be 60. So what does that leave for the third one? 30. And we'll talk about 30, 60, 90, and 45, 45, 90 triangles a little later in the semester. They're special. Last one of these. Line L is parallel to line M. To L and M do not intersect. And finally, L and M are skewed. So which two of those are contradictions? Do 1 and 2 work together? Yeah, they mean the same thing, right? How about how about 2 and 3? Do we remember what skew lines were? Oh, Iris is doing it. So what she's doing is this. Right, so skew lines are in 3 dimensions. But do they intersect? The example I used in class was the C-wing hall upstairs and the main hallway downstairs. They don't intersect, but are they parallel? No. So which two are contradictions? 1 and 3. Because skew lines don't intersect, so those two are true at the same time. 2 and 3 are true at the same time. But skew lines are not parallel. So 1 and 3 would be contradictions. Huh? Skew line, so 1 and 3?
I don't mean specifically this problem. I mean there's a problem. Would it be possible for 2 and 3 and another problem to be?
Oh, sure. Yeah, it just happened that just the way I arranged them, that didn't turn out to be the case. Yeah, there's nothing special about the numbers and the arrangements. All right, let's, now I just want to show you, go step through an indirect proof, how we would use an indirect proof, a very easy example, and then we'll be done. So, we'll do an easy one with algebra. So we're given 5x plus y equals 50, and x does not equal 3. We're given those two things. And we want to prove that y does not equal 7. So indirect proofs are a little different. We don't really do two-column indirect proofs. We can just kind of talk it through or write our explanations. So for this indirect proof, how do we start? What do we assume? Y equals 7. We want to assume the opposite of what we're trying to prove. So assume y equals 7. And then what we're going to do is show that this leads to a contradiction. So what can we do to show that this leads to a contradiction? Plug it into the problem and see what happens. So I'm going to say 5x plus 7, says we're assuming that y equals 7, equals 5. And now we just solve for x. So we distribute here. 5x plus 35 equals 5. Sorry, this should be 50. So add a 0 on the end there. Equals 50. Subtract 35. So I get 5x equals 15. So x equals... But what are we given? X does not equal 3. So y cannot equal 7. That's how we do an indirect proof. Yeah, I like these. So, yeah, they're pretty easy. Not all indirect proofs are easy, but when you can do them, they're kind of nice. My favorite one is that square root of 2 is irrational. You know what a rational number is? Rational means a fraction of integers. So a whole number over a whole number. And you prove that square root of 2 is irrational, that it's a non-repeating decimal. The decimal goes on forever. By assuming that square root of 2 is rational. And then you get a contradiction. It's really nice. That's a fun one. All right, questions there? Okay, so our homework is just going to be practicing what is our first step in an indirect proof, finding contradictions, and then we do a couple of really easy indirect proofs in that. All right, so our homework is page 319. And also, part of our homework is the 5.5 lesson quiz. All right, let me stop this really quickly. Let me